we can show that for an ideal gas, this adiabatic lapse rate is a constant. It's just the acceleration of gravity divided by the heat capacity of air. I might actually show that in the production of the lectures, but I'm not going to do that right now. And for our atmosphere, that works out to be very nearly 1 degree Kelvin per 100 meters. So if I take a sample of air and I displace it upward, without adding or subtracting any heat to it, it will cool at 1 degree for every 100 meters that is displaced. Now, since the buoyancy is related to entropy, we now can understand whether a given state of the atmosphere is stable or unstable. So, for example, suppose the entropy of the atmosphere decreases with altitude. And I take a test sample from near the surface of the Earth, or anywhere else for that matter, and I lift it up adiabatically. It conserves its entropy. And because it conserves its entropy, as soon as you lift it, its entropy will be larger than the environment at the same pressure. And therefore, it will accelerate upward, which is the same direction you pushed it. So this is clearly an unstable configuration of the atmosphere. And conversely, if the entropy increases upward and I displace a sample upward, it would find itself with a lower entropy than that of its environment, and it would accelerate down, which is in the direction it came from. So we would say that that's stable. So we've derived something quite simple about a gas, and that is its stability is related to the vertical gradient of entropy. If the vertical gradient of entropy is negative, the fluid is unstable, and if it's positive, the fluid is stable. Stable configurations of entropy mean that if you displace parcels up and down, they will oscillate, just like the pendulum did. And so a stable fluid supports a spectrum of what are sometimes called buoyancy waves. That is, if you throw a rock into a stably stratified fluid, you can excite a whole spectrum of waves that propagate away. An unstable fluid, on the other hand, convects. And what tends to happen is that warmer fluid from below rises up and is replaced by cooler fluid sinking down. And the effect of this convection is to transport heat upward and to drive the atmosphere back toward a state of neutrality. Convection likes to drive fluid toward a state in which the entropy doesn't change with height. And it's very effective at doing that. So an analogy is boiling water. If you turn up the heat on the stove, the water gets hotter until it reaches the boiling temperature, which is kind of a critical state for that system. And the water boils, and it's almost impossible to raise the temperature higher than the boiling point. It just boils harder. And that's kind of what happens in the atmosphere. So it's very unusual to see states of the atmosphere in which the entropy actually decreases with altitude, because if you did observe such a state, it would be unstable. And to show you that, here are some measurements taken from a instrumented model airplane flying over the deserts of New Mexico on a hot summer day when the ground is being heated, which is trying to drive the entropy profile to a negative entropy gradient. Each of these points represents a measurement of entropy. This is a quantity called virtual potential temperature. I'll probably relabel this graph entropy when I produce it. And this is altitude. And these plus signs represent air, which is sinking, and the dots represent air, which is ascending, according to the airplane. So you can see ascending fluid samples systematically have higher entropy than descending ones. Hot air rises, cool air sinks. Most of meteorology can be boiled down to that statement, it turns out. But the mean profile, the average over this, is fairly constant with height, except when you get very, very close to the surface, and then you start to get very strong gradients because the surface itself is much hotter than the air. So convecting fluids, a signature of convecting fluids in geophysical and astrophysical systems is constant entropy. It's such a universal principle that when the Galileo probe was sent to Jupiter and came back showing certain layers of the Jovian atmosphere had constant entropy, the scientists simply assumed that those must be convecting layers. Even the sun has a constant entropy layer, which is very strongly convecting.